go. All right. So, we're back for more fun and games. Today we're going to be doing chapter 6. All of it. Holy moly. Here we go. So this week is crazy. Chapter 6 today, chapter 7 tomorrow, chapter 8 Wednesday, test on Thursday. Aren't you happy? All right. Vertical and horizontal shifts. Alrighty. All right, chapter 6 is all about transformational geometry. Vertical and horizontal shifts, stretches and shrinks, dilation, reflection, stuff like that, so that you can use mother functions to graph. What did you just say? If you know what y equals x squared looks like, can you graph that in your head, y equals x squared? You can, right? That's a mother function. It's a function you know very well. It's a mother function because it generates all these other functions, like what if I wanted to graph, here, let's try this. What if I wanted to graph y equals x squared? You know how to do that without a calculator, right? The turning point is where? At the origin, 0, 0. And it's what shape? It's a parabola. We don't say U in this room. And what kind of parabola? Is it a smiley face or a frowny face? Or is it hold water, spill water? Have you heard that? It's a hold water, right? Concave up, good, okay. Wait a minute, I don't like that pen. Hang on. Go away. Go far away. Let's make it fat. Let's make it green. Let's make it geometry. Okay. So y equals x squared, you know how to graph it, right? But that's good because now you could do stuff like y equals, wait, hang on. I'm trying to get used to a new, the stylus is almost like it's the same stylus, but I'm trying to get used to it in the new RDP app. What? RDP? Ever hear of RDP? Remote Desktop Protocol. I'm controlling this thing with my Kindle. But it's more responsive than the app I was using last week, so I'm not used to it. But eventually it'll be good. It'll be good. It's a good thing. All right, so anyway, how do you graph this? If you know how to graph y equals x squared, then it's real easy to graph y equals x plus 2. And it's still a parabola. It's still a smiley face. But what changes? It moves to the left 2 units, right. Because if I plug in 0, here, I get 4. But what do I have to plug in to the original equation to get 4? If I plug in 0 over here, I get 0 plus 2 is 2 squared is 4, right? What do I have to plug in here to get 4? 2. So the function value for the new curve at 0 is the same as the function value of the old curve at 2. What if you plugged in 1? What do I plug in 1 into x plus 2? I get 1 plus 2 is 3 squared is 9. So the new equation, if I plug in 1, I get the same y value as if I plugged in what in the old equation? 3. So I'm taking the old equation and sliding it over 2 units. F of 0 becomes my f of 0 is the old f of 2. My f of 1 is the old f of 3. So look what happens in your graph. Let's compare the two. Here, where's my calculator? So if I go to y equals, whoops, turn it on, that would help. Y equals, clear out the stuff. And I'm graphing x squared. Wait, not there. Let me put it there. I'm going to graph x squared. I'm going to graph x plus 2 squared. And I'm going to make the new graph, I'm going to make the original graph thick, so you know which is which. All right, so here's x squared. And here's the other one. It shifted 2 to the left. So that f of 0, the thin curve, right? F of 0 is what f of 2 was. And f of 1 is what f of 3 f of 1 in the thin curve is what f of 3 was on the thick curve. So I'm taking the thick curve and shifting it 2 to the left. All right, so what do you think it's going to look like if I do this? What if I do y equals x? Whoa, what happened there? That was weird. Where did that triangle come from? Right. X minus 3. How about that? What's that going to look like? It's going to go to the right 3. Right? So if I plug in 0, I get negative 3 squared is 9. But in the original equation, I would have to have plugged in negative 3 to get the same thing. So I'm getting at the new y of 0 is the old y of negative 3. So I'm taking the negative 3 stuff and shifting it over to the right 3. Look, take a look at it. Let's graph it. Let's see. How about if I say, let's see, hang on. Where's my eraser? Let me get rid of this guy. So I got curve 1, curve 2, curve 3. How about that? There you go. My geometry disappeared. Dang it. Where did my geometry go? 1, 2, and 3. All right, so let's graph that. So go to y equals, let's change it to the quantity x minus 3 all squared. And graph that. Now, to make that one stand out, let's make it different. How about dotted? There you go. So the original curve is thin. The x plus 2 squared is thick, and the x minus 3 squared is dotted, right? So what had happened was the thick curve shifted over 3 units to the right. Look, where's the turning point on the thick curve? 0, 0. But where is it now on the dotted curve? 3, 0. Moved over 3, right? This is 0, 0. What's this? Negative 2, 0. All right? So, so this shifts 2 to the left from the original graph. Take it and slide it to the left. And this one shifts 3 to the right. Okay. So that's horizontal. That's horizontal shifts. What is this? Okay. All right. That's horizontal shifts. What about vertical shifts? Aha, vertical shifts. By the way, could I do this instead? What if I did this instead? Vars, y vars function 1 of x plus 2. Will that be the same graph? Shifting to the left? There's the original. And here's my shift. That's 2 to the left, right? What did I do? What does this notation mean? How is this different? Before I wrote x plus 2 squared, but now I'm doing y1 of x plus 2. What does that mean? It means take x plus 2 and plug it in. That's a composition of two functions. Say f of x is x squared, and g of x is x plus 2. F of g, plug x plus 2 into x squared. The composition is the translation. So likewise, I could do this. Look, vars, y vars function 1 of x minus 3 would be the same thing as x minus 3 squared, shifting 3 to the right. Yeah, man. There it is. Right? What about this? Let me do something crazy. Are you ready? Oh, you ready? What if you go to stat, edit. Let's edit L1. How about I do negative 3, enter, negative 2, enter, negative 1, and 1, enter, 2, enter, 3. So I entered 6 pieces of data. That's it, just L1. That's all I'm doing. Okay? And then in y equals, do you have that in L1? Follow along with your calculator. All right. So now, how about if I clear this, and I do x plus L1 squared. What's that going to do? What do you think that's going to do? it'll input all the L values. It'll do x plus a negative 3 or x minus 3 and squared, x plus negative 2 or x minus 2 and squared, x plus negative 1 or x minus 1 and squared. And so you'll get all the shifts. So when it's negative, which way are we shifting when we say x minus 3? Which way are you shifting? To the right. If it's x plus 3, you're shifting to the left. So first I'm going to see all the right shifts, because originally, if you go stat edit, I started with some negatives here, so I'm really subtracting. So x minus 3 shifts 3 to the right. Let's see, graph. So first I'm going to see 3 to the right, then 2 to the right, then 1 to the right. Then I have a 1 to the left, 2 to the left, 3 to the left. And they're all thick because I didn't change that. I guess that's okay, I guess. Okay? So, look, what if I did this? Second L1 on the home screen, enter. What just happened? On the home screen, just type second L1, enter. It's telling you what's in L1. You don't have to go to stat edit all the time to see what's in L1, L2, L3, right? You can just do it right there. What about this? Look, what if I did this? Shift, open parentheses, negative 4, comma, negative 2, comma, 0, comma, 2, comma, 4, second close parentheses, stored in L1. What did that do? It changes L1. Stat edit. Right? Look, it changed. So it changes the graph too. Shift 4 to the right. Shift 2 to the right. Shift 0. Shift 2 to the left. Shift 4 to the left. Isn't that what I said to do? Shift 4 to the right. Shift 2 to the right, don't shift. Shift 2 to the left, shift 4 to the left, because I'm graphing x minus 4, x minus 2, x plus 0, x plus 2, x plus 4. What? Arrow, okay. Store. See the store key down here? Above the on key, STO? All right, so you can change the L1 to whatever the heck you want. Let's see. But wait, what if I changed that up? What if I didn't do that? What if I did this? How's that different? Shifts up or down. Because it'll calculate the y value, x squared, then add to it. Now, if you're adding a positive value, it's going to shift up because it's a bigger y value, right? If you're adding a negative L1, it's going to shift down, right? All right, let's see what this looks like. Shift down 4. Shift down 2. See, this is not a good window. Let me go back to zoom 4. Zoom 4. Shift down 4. Shift down 2. Because I didn't change L1. Don't shift. Shift up 2. Shift up 4, you're not going to see it. It's off the screen. If you zoom out a little bit, you'll see it. Zoom out from the origin. Shift down 4. Shift down 2. Don't shift. Shift up 2. Shift up 4. That's hard to see. Let me get rid of thick. How do you get back to normal? There it is. That's normal, right? And let me change the window so that the y's are big, but the x's don't have to be big. I'm going to put the x's back to negative 3.1 for xmin and positive 3.1 for xmax. And see what that looks like. Shift down 4. Shift down 2. Shift down 0. Don't shift, in other words, right? Shift up 2. Shift up 4. Because L1 was negative 4. Shift down 4. Negative 2. Shift down 2. 0. Don't shift. Shift up 2. Positive 2. Shift up 4. Positive 4. Right? Right? Does that make any sense? Right? So you could do crazy stuff like this. What if I said, all right, how about this? Second insert plus L2. And let's make L2 do stuff like second open parentheses is curly brace, negative 3, comma, negative 1, comma, 0, comma, positive 1, comma, positive 3. Stores as L2. What did I do? Oh, I did the wrong parentheses. Second parentheses. There you go. Enter. All right, so what does that mean? L2 is going to be what kind of a shift? If L2 is like 2, x plus 2, what does that mean? Shift up, down, left, or right? Left 2 units, right? And if L1 is 3 at the same time, shift up 3. So I'm shifting horizontally and vertically based on the mother function y equals x squared. You mother function. There's a lot of F words here. What's your favorite F word? 6 letters. Factor. What's your favorite F word? 4 letters. Foil. You mother function. Your lattice rectum. Okay, anyway, we'll get to that. Conics. So, don't mind me. My throat is killing me today. I don't know why. My voice is leaving me. Wait, I must do something about it. There's something in my throat. I don't know what to do. I went to the doctor. She says I'm not sick. I feel like I have a sore throat. She says I'm not sick. So I don't know. All right, so let's see this graph. What the heck is that? What's going on there? No shift at all, right? Oh, look at this. Ah, wow. Because I'm doing horizontals and verticals at the same time, right? So if you go on the home screen and you list L1, the L1 was the vertical shifts. You're adding or subtracting to the y value, the whole thing, to the whole function, right? But the L2 is the horizontal shifts. So if you list L2, at the same time that you're shifting 4 to the right, you're going down 3. These are the horizontal shifts on X, these are the vertical shifts on Y. Right? Did I do that right? No, the L1s are the vertical shifts, sorry. The L1s are the vertical shifts. So when you're shifting down 4, you're shifting right 3. When you're shifting down 4, you're shifting right 3. That's this point right here. So you took the vertex, 0, 0, and you went over 3, down 4. Now what's the vertex? It's not 0, 0 anymore. What is it? You went down 4, over 3. So what's this point? 3, negative 4. That's it. That's what this means. Shift to the right 3, shift down 4 at the same time. From the original, whatever point, let's say 0, 0. Whatever point on the curve, say 0, 0. All right, shift down 1 and shift right 2, right? That's this one. Shift down 1 and right 2. Wait, am I doing this backwards? Wait. L1 is the vertical shifts, right? L1 is the vertical shifts. So it went down 2 and to the right 1. That's what it did, right? Yeah. This is down 2 to the right 1. This is down or up nothing, left to right nothing, right? This is up 2 over to the left 1. Up 2 to the left 1 is this one, right? This guy right here. Left 1, up 2, there it is. Right? Do you see it? So we got all kinds of crazy stuff going on here. What if we changed it around? What if we did L1 here and L2 there? That's a little bit different. Alrighty, so that's how you do horizontal and vertical shifts. But as it turns out, there's all kinds of transformations. Let's see, that was section 6.1. 6.1 is going to talk about horizontal and vertical shifts. 6.2 is talking about reflections. How do you reflect the curve across the x-axis? How do you reflect the curve across the y-axis? Okay. Then 6.3 is talking about stretching and compressing. What if you have a vertical compression or a horizontal stretch? What does that look like? So that's a dilation, right? So you have translations, right? That's the horizontal vertical shifts. You have reflections across the x-axis or the y-axis. You have dilations, stretches and compressions, stretches and shrinks of one, and then mixing them all up. I was starting to mix them up a little bit already. But. All right, so 6.2, reflections. All righty. Let's take a look at the same. How about we change up our mother function? Do you know this mother function? Do you know what that looks like before I hit graph? Y equals x cubed, do you know? Any ideas? What a cubic usually looks like? That weird S shape, right? Sometimes it's bumpy. Sometimes it goes to relative max, down to relative min, like this. But just x cubed, right? Goes like that. Let's see. How about a zoom 4? All right, so what if I just do this? Negative y vars, function 1. What if I just change the sign of all the y's? What's that going to look like? Let's make that thick so we know which is which. So thin is x cubed, thick is the opposite. So what's the relationship between the thick and the thin? Reflection over not the origin, the x-axis. Reflection across the origin would say, take this point 1, 1, and go straight to this point, negative 1, negative 1. That's not what I'm doing. It's taking this point 1, 1 and making it 1, negative 1. It's taking this point 2, 8 and making it 2, negative 8. It's taking this point 1, 1, 1 and making it, 1, negative 1 and making it 1, positive 1. It's taking this point, I said it wrong. It's taking this point negative 1, negative 1, and turning it into negative 1, positive 1. Yeah. And switching the signs of all the y values, not the x values, so it flips the curve across the x-axis. It reflects it across the x-axis. So this branch becomes this branch, and this branch becomes that branch. So f of negative 2 is supposed to be negative 8. Change the sign. F of negative 2 now is positive 8. Okay? Look, it doesn't matter what the mother function was. What if I started with the parabola? Okay, let's see. Here's your standard parabola, and here's the reflection. All right, so what is negative f of x compared to f of x? A reflection across the x-axis. But what if I didn't put the negative there? What if I put it there? Second insert a negative. Any ideas? F of negative 2 becomes f of positive 2. F of positive 2 becomes f of negative 2. Now I'm not reflecting across the y-axis. Looks like it didn't do anything. Is that what happened? It didn't do anything? Why didn't I see anything different? I got the same graph twice, didn't I? It overlapped, yeah. Yeah, okay, so what if I change the mother function? What if I make it a cubic again? The thin is the original, the thick is the translation, or the transformation, I should say. It looks the same as last time. It looks like it's reflecting across the y-axis again. Let's say the x-axis again. Is that what it's doing? It's not. Change the mother function. Make it really different. How about, let's make it, I don't know, sine of x. Here's the mother function. Here's the transformation. What's it doing? It looks like a reflection across the x-axis again, right? But the problem with this is the symmetry. It's hard to tell because of the symmetry. Y equals x squared has y-axis symmetry, right? Y equals x cubed has origin symmetry. So if it reflected across the y-axis or if it reflected across the x-axis, it looks the same. What does origin symmetry mean? Look, so does this. The sine curve has origin symmetry. In other words, let's see, I think this is pi over 4. The sine of pi over 4, do you know what the sine of pi over 4 is? No, you're converting radians to degrees. All right, let me say it a different way. Do you know the sine of 45 degrees? No, that's a sine of 30. Huh? Right, 2 over 2. So this is what it's saying. F of 45, this is 45 degrees, in this case it's pi over 4 radians, is rad 2 over 2. Now what did I do? I changed the sign of the x's. So, if f of pi over 4 is rad 2 over 2, then f of negative pi over 4 is rad 2 over 2. If f of pi over 2 is 1, wait, if f of Wait, what's my scale? My scale's messed up. Oh, that's what's messing up. Let me do a zoom trig. Zoom trig. Here's sine in zoom trig. And here's y of negative x. Okay? What's going on? What's happening is that the sine of pi over 2, what's pi over 2 in degrees? Pi over 2 radians? 90 degrees, right? So the sine of 90 is 1. You see the 1 here? This is 90, because if I do the window, it's going from roughly negative 2 pi to positive 2 pi in pi over 2 increments. Pi over 2 being 90 degrees. Pi over 2 radians being 90 degrees, right? Why am I talking about this? Because chapter 7 is trig, warming you up for tomorrow. Okay. All right. So if the sine of pi over 2 is 1, the sine of negative pi over 2 is 1. Which way is it reflecting? If the sine of pi is 0, the thin one, the sine of pi is 0, the sine of negative pi, the thick one, is also 0. Am I reflecting across the x-axis now? I'm reflecting across the y-axis. It's hard to see. Let's see. What if I made something completely different? How about just a line, 2x plus 5. Now that's a mother function, right? Can you graph y equals 2x plus 5 in your head? How do you graph y equals 2x plus 5? You start at 5 on the y-axis and you count off a slope of up to a 1, up to a 1, right? So you have that in your head? Okay. Now I'm going to compare that to changing all the x's to their opposites. Here's the mother function. Here's the reflection. Is it reflecting across the x-axis now? No, it's reflecting across the y-axis. If f of 2, let's see, what if I plug in 2? 2 times 2 is 4 plus 5 is 9, right? So if f of 2, it's off the screen. Dang, it's hard to see it here. How about f of negative 1? What's f of negative 1? 2 times negative 1 is negative 2 plus 5 is 3, right? So if f of negative 1 is 3, let me do a zoom 4. The scale is weird. Come on, today. If f of negative 1 is 3, now the new f of positive 1 is 3. If the f of negative 2 is 1, then the new f of if the f of negative 2 is 1, the new f of positive 2 is 1. I'm reflecting across the y-axis. As opposed to this. What's going to happen now? I'm not changing the x's sign, I'm changing the y's sign. So that reflects across the x-axis. Let's see that. There's the original function. There's the reflection across the x-axis. And when they hit the x-axis, they have to match, right? They're going to intersect there. So instead of f of 1 being 3, f of 1 is negative 3. If instead of f of negative, I'm saying it wrong. Instead of f of negative 1 being 3, f of negative 1 is negative 3. Instead of f of negative 2 being 1, f of negative 2 is negative 1. I'm changing the signs of the y's. So it doesn't matter what the mother function is, but notice if the mother function has y-axis symmetry, what happens if you're reflecting across the x-axis? Right? But what if it has y-axis symmetry and you're reflecting across the y-axis? Delete that. Ah, dang it. Vars, y vars, function 1 of negative x. Where's my x? Here's the mother function, and here's the reflection. I don't see nothing. Why? What happened? I'm changing the signs of the x's, right? So it's reflecting across the y-axis, right? So f of 1 is 1 turns into f of negative 1 is 1. If f of 2 is 4, then f of negative 2 is 4. It's an even function. Even functions have y-axis symmetry. When you reflect them across the y-axis, it looks the same. Look. What if I make this thick? Here's the mother function, and here's the reflection. It looks like the same curve, but it's reflected on top of itself. Okay. Now, what if I change it to an odd function? Okay, you said even odd. Okay. What about an odd function? And now I'm reflecting across the y-axis still. Here's my odd function. Here's reflecting across the y-axis. Okay. But what if I reflect across the x-axis? Here's the mother function, and here's the reflection. So, since it didn't overlap, since it wasn't the same, does it have y-axis symmetry? When it reflected across the y-axis, it was different. Does it have y-axis symmetry? No. If you reflect across the y-axis and it's the same, you have y-axis symmetry. If you reflect across the x-axis and it's the same, you have x-axis symmetry. What this has is origin symmetry. This is origin symmetry. Ready? If you change the signs of the y's and the x's, here's the mother function, and here's the reflection. I'm reflecting both across the x and the y. That's called origin symmetry. So that f of 1, if f of 1 is 1, f of negative 1 is negative 1. If f of 2 is 8, f of negative 2 is negative 8. It's reflecting through the origin to the other side. Okay? So when we talk about reflection, we can also talk about symmetry. You have x-axis symmetry, y-axis symmetry, and origin symmetry. Okay? Let's write that down. Let's see. Yeah.
So if it's negative f of x, it's a reflection across the y-axis, and if it's f of negative x, it's a reflection across the x-axis?
Right. So, let's see. How am I going to write this? If you convert f of x to f of negative x, you're reflecting across the y-axis. Y-axis. I need an eraser. Y-axis reflection. Okay? If you change f of x to negative f of x, what do you get? If you change the sign of the y's, in other words. If you change the sign of the x's, you're reflecting across the y-axis. If you change the sign of the y's, you're reflecting across the x-axis. So that's x-axis reflection. But what if you change the sign of both? What if you change f of x to the opposite of the y's and the opposite of the x's? That's origin. That's right. That's origin reflection. Reflection across the origin. Yeah, actually, yeah. But we're not going to talk about rotation in this context. Okay. Now, you know what? That's good. The stylus is very responsive with this app I'm using called Splashtime. What sucks is my handwriting. Okay. Sorry, that's the way it is. All righty. So when do you have an even function? This is an even function. Give me a pen. Where did my pen go? Okay. An even function happens if, when you change the sign of the x's, you get the same function that you started with for every single x. So like when you took the parabola and you reflected it across the y-axis, it looked the exact same way because it is. It's the same function. Okay. When do you have an odd function? Let's see. When do you have an odd function? When f of negative x is negative f of x. Okay? In other words, you're changing both signs. That's reflection across the origin. All right, so let's see. even. That's origin. All right, so for example, let's say I gave you some functions. Let me ask you. Is y equal to, whoops. Is y, wow, what happened there? Whoa, stop it. Okay. So, yes. Is y, why is it stuck? Okay. All right. So, if y, why is this, it's stuck doing something weird? Hang on. Is that right? Yeah. It went into mouse mode, now it won't let me write anything. Hang on. Alright, so I got geometry on, I got thick pen, I got green, right? Okay. So what if y, I can't write, what's going on? It won't let me write. Why won't it let me write? Shift control, I don't want that. Okay, there it goes. What if y is the absolute value function? You know what that looks like? That's another mother function. You should know what it looks like. What does it look like? It's like a V, right? Again, it goes through 0, 0, but it looks like y equals x in the first quadrant. It looks like y equals negative x in the second quadrant, right? Right. If do you know how to graph that on a calculator? Why? How do you do that on a calculator? You know? Y equals what? Math. I think it's under num, absolute value. There it is. So if you graph that, zoom 4, that's what it looks like. Now you tell me, just from the graph, can you tell me if that's an even or an odd function? That's an even function that has y-axis symmetry. Okay? All right, let me define it this way. What if I call that f of x? What's f of negative x? What does it mean, f of negative x? What do you do? How do you calculate f of negative x? You take negative x, you plug it in wherever you saw x, okay. But what's the absolute value of a negative? Well, technically it's no sign, but yeah. In other words, the negative goes away, doesn't it? So is it true that is this true? Is f of negative x, in fact, the same thing as f of x? That's when you have an even function. Okay? So therefore, even function. Okay? All right, so like we said, if f of negative x is the same as f of x, you have an even function. It means y-axis symmetry. If f of negative x becomes negative f of x, that's origin symmetry. Okay? All right, so in either case, you plug in negative x to see what happens. Okay. So how about this one? What if I gave you, let's go to another page. What if I said, what if g of x is 1 over x? What's g of negative x? What do you do physically? You take the negative x, plug it in for x. You keep on doing that. Okay. 1 over negative x. But what is that in relation to g? What's 1 over negative x? Is that g of x? Like last time? We found that f of negative x was f of x. Well, am I getting that this time? Is it g of negative x the same as g of x? No, what is it? They are related. What's 1 over x compared to 1 over negative x? How are they related? aren't they the exact opposite? In other words, negative g of x? Didn't we say that when we have g of negative x is negative g of x, if f of 2 is 8, then f of negative 2 is negative 8, right? Yeah, all right, let's put it this way. Let's do something. If f of 2 is a half, isn't it? If I plug in 2, I get a half. F of negative 2 is negative a half. In other words, you're taking the point 2, 1 half, and you're reflecting across the origin to negative 2, negative 1 half. So it reflects the point from the first quadrant through the origin to the third quadrant. Look at it on Ziggy. Do you know what that looks like, 1 over x, if you graph it? Eventually that's going to become a mother function. Maybe it's not yet, but it's hyperbolic. You ever hear of a hyperbola? Hyperbola has 2 branches. There they are. Isn't it true that any point you pick on here, if you reflect it through the origin, the same distance, the same direction, you end up on this branch? So that f of 2 is a half, reflects to f of negative 2. F of negative 2 is negative a half. See what's going on? F of 2 is a half, isn't it? So reflected through the origin is over here. Isn't it f of negative 2 is negative a half? How about f of 1 is 1? F of 1 is 1. Reflect through the origin. F of negative 1 is negative 1. So f of negative x is negative f of x. F of negative 1 is negative f of 1. F of negative 2 is negative f of 2. That's what makes it odd. So if you have origin symmetry, if your graph has origin symmetry, it's an odd function. Alrighty. Is that true for, give me another odd function. What's obviously odd? X to the 3 or something, right? When they say odd or even function, it means that it can be written as a power function with an odd or an even exponent, right? This one's not obvious. But this one should be. What if I said h of x is x cubed? What's h of negative x? What do? You plug negative x wherever you see x, and now you cube it. But you know what happens to when you cube a negative? What do you get? It stays negative, right? The cube of negative 2 is negative 8. The cube of negative 3 is negative 27. The cube of positive 2 is positive 8. All right, so it's going to be the opposite of x cubed. Okay? So whenever we get the opposite of the original function, the opposite of the x cubed, right? That's what kind of symmetry? Origin symmetry. That's an odd function, all right? So in this case, I could say it's an odd function, or I can say we have origin symmetry. In the previous example, I could also say I have an odd function, or origin symmetry. It means the same thing. But in the first example, we had an even function, right? We had an even function. So let's say that's y-axis symmetry. It's a reflection across the y-axis. Some people call that vertical symmetry. Okay. All right, so what if I gave you something completely random? Let's see if we can test it. What if f of x is something random? Negative x cubed minus 3x squared. How do we test for symmetry? Let's say I want to know what the symmetry is. Is it symmetric about the y-axis or symmetric about the origin? By the way, you can't really be symmetric about the x-axis and still be a function, right? If you have a function that's symmetric about the x-axis, let me digress for 1 second. What if I graph this? No, not that. What is this? Wait. Where's my undo? Undo, undo. Where's my geometry? There you go. What if I graph this? And let's say, I didn't draw it too good, but let's say it has x-axis symmetry. Is that a function? Is it? No, it's not. Because to be a function, it has to pass the vertical line test everywhere. Every x value has to have one unique y value. F of 2 can't be 4 and negative 4 at the same time, for example, right? Right? So if you have x-axis symmetry, you're not a function. So we're talking about symmetry of functions. So it doesn't make sense to talk about x-axis symmetry for a function. It makes sense to talk about origin symmetry for a function, an odd function, or y-axis symmetry for a function, even function. But this is not a function. So we're not talking about that here. All right, so how do you test for symmetry? You plug in what? Negative x. So f of negative x is going to be negative x cubed minus 3 times negative x squared. Okay. So the question is, there's three possibilities. Either you get the same thing you started with, which is y-axis symmetry, f of negative x equals f of x, or you get the opposite of what you started with, origin symmetry, f of negative x is negative f of x, or you get something completely different, it has no symmetry at all. Okay? So you tell me, where's my pen? It's not giving me a pen. This, okay. Okay, so you tell me, what is negative x cubed, by the way? Negative x all cubed is negative x cubed, okay, like before. All right, so it looks like we're getting the same as what we started with. Did we start off with negative x cubed? But what's negative x, the negative x squared? Just x squared. So, hang on. Oh, I thought, oh, okay, all right. So what are we getting? We got the same thing, right? What does that mean? When f of negative x equals f of x, is that an even function or an odd function? Even. Is that y-axis symmetry or origin symmetry? Y-axis symmetry. Okay. I thought this was going to be, I did something completely random. I thought it wasn't going to have any symmetry. Let's see that that does in fact have symmetry. Okay. Negative, let's graph it. You're saying it has y-axis symmetry, right? All right, so negative x cubed, what was the original thing? Minus 3x squared, right? Minus 3x squared. How about a zoom 4? Look, it has y-axis symmetry, look at it. Let's zoom out a little bit. Zoom out. Oh, no, it doesn't. Wait a minute. What happened here? Something weird happened here. Hang on. Oh, my goodness. You know, hang on. I thought I turned this damn thing off. Wait, did I do something weird here? This is not showing what I wanted to show. Negative x cubed minus 3x squared doesn't have y-axis symmetry and it doesn't have origin symmetry. It has neither, right? It doesn't. So, remember what we said. If it has y-axis symmetry, right, if it's even, if it has y-axis symmetry, f of negative x is f of x. If it's odd, f of negative x equals the opposite of f of x. What did we get? We got that f of negative x is negative x cubed minus x squared. Whoops, it's squared here. But that's the same thing as f of x. So that should be y-axis symmetry, right? Did we do something weird? Negative, oh yeah, we did. Look what I did. What did I do wrong? Oh, bad teacher. Bad teacher. What did I do wrong? I plugged in negative x to cube it, right? But what happened to this negative? It was here already. I lost it. It should be in front. Whoops, sorry. I didn't copy it right. All right, so let me fix that. So how are we going to fix that? Let's get an eraser. Let's get rid of this part here. All right, let's get a pen. I get rid of that part there. Get a pen there. Yeah, it is a negative x that we're cubing, but there's a negative in front. So negative x cubed is negative, but the negative in front cancels it. Ah, that's why it's not. So they're not the same. So remember, if negative f of x was the same f of x, it's not y-axis symmetry. If negative f of x equals negative f of x, the total opposite, not only the first term changes sign, but the second term changes sign, then that's origin symmetry. But it doesn't. That's why it looks wacky. That's not a mother function. That's a wacky function. Okay? All right, so as we expected. Okay, that's good. All right, that's section 6.2. Aren't you happy? That was neither, right. So yeah, when they answer the question, they're going to say, is it even, odd, or neither? Or does it have y-axis symmetry, origin symmetry, or no symmetry? That's the kind of question they'll say. Just three choices, yeah. In this case, neither. Right. Okay. All righty, good. What else we got here? Okay, how about dilation, stretching and compressing? Stretching and compressing. All right, let's take a new mother function. Let's see, what mother function? This one's fine, x squared. All right, there's my mother function. Now, instead of adding to the x's or subtracting from them, remember when you add to the x, shifts to the left. Subtract from the x, shift to the right. Add to the y, shift it up. Subtract from the y, shift it down. How about instead of adding and subtracting, I'm multiplying and dividing instead? What happens? Okay? Let's say I graph this. L1 times y1. And let's make a new L1. I don't like that L1. How about we make L1, I don't know, second open parentheses is a curly open, 1, comma, 2, comma, 3, just that. Then close it and store it as L1. So my L1 changed, right? All right, so now what am I doing? I'm graphing L1 times y1. So L1 times y1. y1 is x squared, and L1 is 1, 2, or 3. So I'm graphing 1x squared, 2x squared, 3x squared, right? What happens if I take the y values that I had, x squared, and I multiply by something? All right, so this time I'm going to make the original curve thick and graph. So here's the mother function. And one of them is overlapping, I think. Then that's 2 times. Then that's 3 times. What's going on? Huh? What? They're getting thinner. It looks like a horizontal compression, but no. This is considered a vertical stretch. The y values are getting bigger. For the same x value, the y value is getting bigger. If x is 1, when you square it, you get 1, right? But if you multiply by 2, you get 2. You multiply by 3, you get 3. It's stretching the y values. So it looks skinny, right? But what it's doing is stretching the y values, making it taller. It's dilating it vertically, okay? So it's a vertical stretch. What if I didn't do multiply by L1? What if I took the y values and divided by L1? Let's see what it looks like. Here's the original. Then dividing by 1 is the same. Then dividing by 2, come on. Dividing the y's by 2, there you go. And then dividing the y's by 3, there you go. So it's taking the y values and making them smaller. That's a vertical shrink or a vertical compression. Okay? So if y of 2 was 4, then y of 2 over 2 is 2. Y of 2 over 3 is 4/3, is what's happening. Okay? Okay. You don't see it? All right, look, let's do this. What if I said, where's this is my compression, right, at y2? What if I said y2, y-vars function 2 of 2? What happened? likewise, if I make y3 with what we used to have, L1 times y1, that's the vertical stretch. It looks like it's getting skinny. The one you don't see, then the 2 times, then the 3 times, there it goes. So if you go on the home screen, vars, y vars function 3 of 2. What's happening? Remember y2 was x squared over L1. Divide by 1, divide by 2, divide by 3. y3 was x squared times L1, times the 1, times the 2, times the 3. So if y1 is x squared, when you square 2, you get 4. If you divide it by 1, you still get 4. If you multiply by 1, you still get 4. But if you divide by 2, you get 2. If you divide 4 by 2, you get 2. If you divide 4 by 3, you get 4/3. If you multiply the 4 by the 2, you get 8. If you multiply the 4 by the 3, you get 12. So the y values are getting bigger when you're multiplying. The y values are getting shorter, right, when you're dividing. Right? All right. But notice that L1 has all numbers greater than or equal to 1. What if it was the reverse? If I divide by numbers bigger than 1, your y values are getting small. If I multiply by numbers bigger than 1, your y values are getting bigger, so that's a stretch. Right? If you divide it by numbers bigger than 1, the y values are getting smaller. Vertical shrink, vertical compression. The book uses the word compression. I tend to use the word shrink, same thing. But what if these numbers were less than 1? It would be the exact opposite, right? So if I'm dividing by a number less than 1, it's going to get bigger. If I'm multiplying by a number less than 1, it's going to get smaller. It's going to be reversed. So what if I change the L1? Let's say I make L1 equal to this. Curly brace. Let's say 1/2, comma 1/3, comma 1/4. Or if you want decimals, you get 0.5, 0.25, whatever, right? And whoops, curly brace, close it. Let's store that as L1. And let's graph that. Well, it doesn't think I want to graph it until I change something here. Regraph, there you go. So there's your mother function. Hello. Times the 1/2. Times the 1/3. Times the 1/4. Okay. Divided by the 1/2. Divided by 1/3. Where's the 1/4? I didn't see it, but anyway. Okay? So if you're dividing by a number smaller than 1, that's a stretch. If you multiply by a number smaller than 1, that's a shrink. Right? No? Because if you divide by half, you're really multiplying by 2, reciprocal. If you divide it by 3, you're really multiplying by... If you're dividing by a third, you're really multiplying by 3. The reciprocal, right? Okay. All right. That's all there is to vertical stretches and compressions, I think. Anything else interesting going on there? No. All right, so that's it. All right, now what did we just do? We multiplied the y values. What if we do the same thing to the x values? 6.4. What if we do the same thing to the x values? All right, let's do a different mother function. How about, all right, clear this, clear this, clear this. What if I do, I don't know, e to the x? How about that? Now, e to the x should be a mother function too, right? Is it exponential growth or decay? Growth, right? If I plug in x equals 0, you get, what's e to the 0? 1. So it's a y-intercept of 0, 1, right? What's the domain? What x values are you allowed to plug in? Are there any x values that are bad? That gets you undefined? No, right? What's the range? It's all positive y values are greater than 0, right? Do you know what it looks like? Right? It does asymptotic to the x-axis as you go to negative infinity, and then goes to positive infinity. The y values go to positive infinity as the x values go to positive infinity, right? All right, so there's my mother function. Now what I want to do is, instead of multiplying the whole thing by L1 or dividing by L1, I want to multiply or divide the x value, sorry, the x values by something, okay? So how about if I say, what's e to the what's e to the well, wrong one. E to the, where's e to the L1 times x. And let's make L1 something easy. How about curly brace 2, comma, curly brace 3, whoops, comma 3, comma 4, close the brace, store that as L1. There you go. All right, so L1 is 2, 3, 4. So what happens, compare e to the x to e to the 2x, e to the 3x, e to the 4x. What's going to happen? As you multiply x by bigger and bigger numbers, look what happens. There's your mother function. There's e to the 2x, e to the 3x, e to the 4x. So for smaller values of x, you're getting bigger values of y. It's taking the y values here and moving them closer to the origin. Taking the y values out here and moving them here, moving here, moving them, moving them. That's called a horizontal shrink or compression. Horizontal shrink or compression. What if I divided by that instead? Right? So notice what I'm doing. I graphed y1 is e to the x, right? Let's make that one bold so it sticks out. That's y1, the bold one. Now here's y2, e to the 2x, e to the 3x, e to the 4x. So it's taking the same y values but shrinking them, getting them closer to the x-axis. It looks like a vertical stretch, but it's a horizontal shrink. All right? What if I divided by those numbers instead? So y1 is e to the x, but then y2 is e to the x over 2. So I'm dividing by 2. E to the x over 3, I'm dividing by 3. E to the x over 4, I'm dividing by 4. It's like I'm multiplying by half. If I'm dividing by 2, I'm multiplying by half, right? If I'm dividing by 3, it's multiplying by a third. If I divide by 4, it's multiplying by a quarter. So I'm multiplying by smaller and smaller numbers in front of the x. So instead of compressing, what do you think it's going to do horizontally? It's going to stretch. Let's see that. Here's the original mother function. That's e to the x, and here's e to the x over 2. Here's e to the x over 3. Here's e to the x over 4. It's going through the same y-intercept, 0, 1, but it's stretching out for smaller, for bigger x values to get the same y values. Right? So it's stretching out the domain. It's blowing it up horizontally, right? So that's your horizontal and vertical shifts. Oh, sorry, stretches. Alrighty. So now what if you want to put it all together? What if you had like a whole bunch of stuff mixed together? All right. Let's say I wanted to graph this. Not that. That's not a function, right? All right. So what if I gave you f of x equals 5 times x plus 2 squared plus 7. So notice there's a whole bunch of transformations going on here. What does the plus 2 do? First of all, who's the mother function? This is all based on what function you can graph in your head. The parabola y equals x squared, right? Okay. So take the parabola y equals x squared in your head, and what does the x plus 2 tell you to do? Shift it 2 to the left. What does the 5 tell you to do? It looks narrow, but what it is a vertical stretch, making the y values 5 times bigger than they would have been. And what does the plus 7 do? Goes up 7. All right. Can you do that by hand? Do you need a Ziggy for this? Let's see. Let's graph this all by hand. First, I'm going to take this and change it to this. Right? How do you do that? You take, wait, I keep on losing my geometry. Put it on. Okay. You take y equals x squared, roughly, right? And you're shifting it which way did you say? 2 to the left, okay. So instead of going through 0, 0, it's going through 0, 2. And what's the y-intercept going to be? In other words, I know the x-intercept, it hits 0, 2, 0, right? But what's the y-intercept going to be? When you plug in 0, you're going to get 4, right? Because if you go 2 to the left, if you go 2 to the left here, it's like I'm physically taking this point that's here. It won't show me the point. That point there, at -2 what? What's that point? -2 what? If I plug in -2 into the first function, what's -2 squared? 4. I'm physically shifting that 2 to the right. So -2, 4 becomes what? If you go 2 to the right, -2, 4 turns into 0, 4. So that's the y-intercept. Okay? So it's going to go through that point, and I can't draw it very well on here, but you get the idea. All right? So I'm physically shifting that. I don't like that. Oh, to the left, I'm sorry. Yeah, to the left. I'm thinking I gave you a different question. I gave you +2, didn't I? Yeah, I did. Okay. All right, so it's to the left. I'm sorry, to the left. Ding, ding. So it's going through that point and that point. It's not to scale, but...
So what's the y-intercept?
Well, what I did was I said I'm taking a look at some important points. The only thing I can say about the original parabola is that 0, 0 is the x-intercept and the y-intercept both, right? So when you shift that 2 to the left, you go to where? Where does 0, 0 end up if you go 2 to the left? No. If you're taking this point, 0, 0, right here, this point, and you shift 2 to the left, it's a -2, 0, right? Wow, this is a mess. All right, anyway, you get the idea. All right, so it's going through this point here, right? But then I'm saying, well, can't we figure out the y-intercept the same way? That's if you take a point 2 to the right over here and shift that 2 to the left. All right, so what point is that? If I plug in 2, I get what? 2 squared? 4. So this point is 2, 4. I meant not that point, I meant this point. This point is 2, 4. Shift that 2 to the left, and what does that become? 0, 4, which doesn't look like this, but... Wait, hang on. Doesn't look like this at all. Let me get rid of this. The idea being that this is now 0, 4, and this is now -2, 0. All right? So you get the point 2, 4 becomes the point, let's make that stick out, 0, 4, and the point 0, 0 becomes the point -2, 0. I'm not liking this part here. Why is this not working? There you go. See the point? See what I'm saying? So you take 0, 0, and shift it 2 to the left. You take 0, 4, sorry, 2, 4, shift it 2 to the left. All right, so now that's a complete graph. It's a parabola. You see the min, the turning point. You see where it's increasing, decreasing. You see the concavity. You see both intercepts. That's a good graph. All right, now, what does the 5 do? What's the 5 going to do to this? First I did the x plus 2. Now I'm going to, right, I did the x plus 2 to the x squared. Now I'm going to do the 5 times the x plus 2 squared. Huh? Stretches the y's. So instead of going through 0, 4, what do you think it's going to go? 0, 20. There you go. That's it. Okay. So now I'm going to say, okay, I'm still going to go through the point. Why does it keep on turning off the geometry thing? Stay on. Okay. All right, so it's going to look similar. It's still a parabola like this. And this point is still negative 2, 0. Why? Why is that point not changing? Because I'm multiplying the y's by 5. But the y is 0. So 0 times 5 is still 0. But this point up here, I should have made it more stretchy, shouldn't I? Hang on. I should have erased that part. I want to undo that. I want to undo that. I want to do that. Okay, I should have made it more stretchy, right? So this is still going to be negative 2, 0. But this becomes 0, yellow. This becomes 0, 20. Okay? All right, so now, what's the last thing they wanted you to do? The plus 7. What's that going to do? It shifts everything up 7. So this becomes negative 2, 7. This becomes 0, 27. That's how you do it. Okay, there you go. So let's make room for that graph. That point is going to be negative 2, 7. And that point's going to be 0, 27. Wow, that's bad. I don't like the 7. I don't like this. And so this point, we're talking about this point, is negative 2, 7. And this point, it's not drawn to scale, obviously, is 0, 27. All right, so notice how we did this. We did this sort of like order of operations. We did this from the inside out. We did the parentheses first, the plus 2. We did the multiplying next, times 5. We did the adding last, plus 7. It's sort of like go from the inside of the parentheses, work your way out, because if you don't do it in the right order, you might get a different graph. All right, so let's do this exact same thing on Z. All right. Let's see if we did this right. Let's check it. Okay, so I'm going to clear all this. I'm going to clear all that. All right, so my mother function was this, right? And the first thing I did, I'm going to turn that off. I'm going to keep it there. I'm going to use it here. I'm going to say vars, y vars, function 1 of x plus 2. That's the first transformation we did. We shifted everything 2 to the left. Zoom 4. So is that 2 to the left from the original graph? You want to see the original graph? We can put the original graph on. Okay, let's make the original graph thick. So here's the mother function, the thick one, right? Then 2 to the left. We said that, right? Then we said, okay, what if I do the times 5? It's still going through negative 2, 0, but then it ends up going through 0, 20. Is that true? Let's see. Trace. On y1, it's 0, 0. Down arrow. On y2, it's 0, 20. Right, it's off the screen, but there it is. You can still trace it. All right, and then plus 7. And here's some other function. And here's the transformation, but you don't see it. Why not? Because y max is 3.1, but the bottom is now at 0.7, right? So I have to make the window go up to at least, what was it, up to 27? All right, so let's go up to, it's not going to be a square window, but go to 27. Here's your mother function, shifted 2 left, stretched 5, up 7. Does it go through negative 2, 7? Let's find out. Trace, that's y1. Down arrow, that's y2. 0.27 is the y-intercept. Let's trace back to negative 2. Does it go through negative 2, 7? There he goes. So it's shifted to the left, it's stretched vertically, and then it's vertically shifted also. It's horizontal shift to the left 2, stretch by a factor of 5 vertically, and then shift up, vertical shift, translation I should say, up 7, right? So we graphed all of that by hand. Do you need a Ziggy? No, not really. But you can use Ziggy to check you want, okay? Alrighty. So, horizontal and vertical translations, horizontal and vertical stretches, reflections across the x-axis and y-axis in symmetry, and mixing them all up. That's the entire chapter 6. I'm done. I'm done with recording anyway. So, let's say goodbye to YouTube. Bye-bye.